O meu ano vai trazer muitas perguntas e difíceis.
Tomara que não.
It's about the programming and all this.
Francisca, não está passando.
É porque eu estou a mexer aqui. Mas
ok.
Já te...
Good morning, everybody, here and outside. So I'm here on behalf of Professor Aldina, who could not come today, to continue with another session of these presentations by our students and PhD students, also other people in this Friday at ISISE today. So today we will have a presentation by Fernando Ribeiro, which is about development of finite element design methodology for steel joints. So this is yours, and we have about 20 minutes here for this presentation. Thank you.
Thank you, Professor. Good afternoon, everyone. My name is Fernando Ribeiro, and the title of my thesis is Development of a Finite Element Design Methodology for Steel Joints. My thesis is under supervision of Professor Luis Simões da Silva, Professor Traiana Tankova, and Professor Jorge Coelho. So just to give a general overview of my work plan. So my work plan is divided in 5 tasks, and today I will be focused on these 3. So task 2, 3, and 4. This presentation is divided in 8 parts. So due to the growth of the computational capacity of the computer softwares over the last years, several finite element software have been developed. So several studies have been conducted, and this consists of an efficient approach for analyzing structures. So new codes and modern codes, such as the new part of the Eurocode, the 1.14, provide guidelines for numerical methods in the design of steel structures. So the main objectives of my research are to develop and implement 3D models of joints at both component and joint level, analyze and reformulate analytical models available in the standard, and develop and propose new methods for the design of steel beam-to-column joints. So the component method is a well-known method, and it's currently applicable to the part 1.8 of the Eurocode 3, and is done consists of joining a set of individual basic components which are idealized springs. So this method is divided basically in three parts, which consists of the identification of the main components, the evaluation of the individual components, the main characteristics, and the assembly of the components into a mechanical model. So these are the expressions from the Eurocode, and here is a comparison between the old Eurocode and the old Eurocode and the new Eurocode, and the differences are highlighted. So for the components of beam to column welded joint, so as you can see, there is no difference for these last two components. Going to the numerical modeling part, so I've developed numerical models in Abacus, the commercial finite element software, for the components of the web panel. So we have components for the column web intention and column web compression. So starting from the column web components in tension and compression, so we considered two symmetry planes, the XY and XY, as depicted in this figure, to simplify the model and to make the analysis go faster. And you can have also a finer mesh. The material properties are the quadlinear model from the new Eurocode, part 114. And the static general analysis has been conducted including nonlinear effects. So you have the stress strain curves for the high strain steel material as 690. Regarding the boundary conditions you have on this figure on the right, so these are the boundary conditions applied along with the symmetry conditions. For the geometric imperfections, the first buckling mode of linear buckling analysis has been considered with an amplitude of dc over 200. And on this figure you have the influence of the mesh size. So as you refine the mesh, considering this option or glass enhanced, which I will explain later, as you refine the mesh, you get the curve tends to go down at this later part. So this happens for the column web intention, and for the column web compression, this difference is not so significant. So we need a finer mesh in this region due to stress concentrations. So the mesh size we consider is this approach with a refined mesh close to the wells. So this is a mesh sensitivity study for the column web intention, considering several types of elements. So linear, quadratic elements with hybrid formulation and with incompatible modes, and also with this option or glass control enhanced on default or on enhanced. So by this we came up to the conclusion that the most suitable option would be the C3D8R, which is the default element, solid element in Abacus, and with the or glass control on default, but with a mesh based on this approach of having a finer mesh close to the wells. For the column webbing compression, as I said, there is no huge difference between the varying the element types and even the mesh size. So we decided that for this case, this option is already a good option. Regarding the modeling of the beam to column welded joints, so we've developed a hybrid model with solid and shells. The static general analysis has been conducted as well. Rigid body and shell to solid coupling has been applied on this interaction between the shell and the solids, and we have a solid core with a finer mesh, which we have is the region which interests us the most. So the boundary conditions are pinned and are depicted on this figure. And transverse stiffness have been applied and have the same dimensions as the beam flange, as depicted on this figure. So for the element type, we decided to go for linear elements, for shell and solid elements, and regarding the mesh, it's considered at least 4 elements across the thickness, and the mesh optimization is done through an iterative process, which is done in Python until reaching a certain number of nodes in the total mesh. So we're using refined mesh for region of stress concentrations, and the mesh quality is evaluated through the aspect ratio. So you can see on this plot an image of an example of a mesh, and as I said, we're considering a refined mesh, especially in this region. So these are the distance that we consider for each element. We also conducted a mesh sensitivity study for these models as well. So you can see that the mesh size doesn't have a large influence in the shape of the curve, of the moment rotation curve. But you can see that there is this difference in the moment, the resistance. So this moment has been determined using the plastic strain criterion of 5%. So as you refine the mesh, you get smaller values for the resistance according to this criterion. For the element type, there is no difference as well in the shape of the curve. But we have for the quadratic elements, we have this difference in the moment resistance. Okay. Regarding the imperfections, it's considering the first buckling mode from linear buckling analysis as well, the same as done for tension and compression. And these are the boundary conditions which were applied. So a rigid body constraint is applied to the beam, and shell to solid coupling, rigid body to the extremities, and only the web panel is free to move according to these boundary conditions. So that we get these shapes of for the first buckling move for unstiffened and stiffened joint. So talking a little bit about Python scripting. So these models are generated automatically through Python. There is an Excel spreadsheet in which you input the geometry, the material properties, all the parameters that you want for the model. Then a Python script reads this Excel and generates the model, this model with solid and shell elements, with all the constraints and boundary conditions. We also have a script for running and monitor the analysis simultaneously. So we run the analysis until a certain level of strain is reached in a certain region you can determine. The results are automatically extracted as well. So you can extract forces, displacement, stresses, strain. Going to the validation of the models. So these 3 welded joints from Sandra Jordão in S355 and roller profiles were selected. So the column has 3 meters and the beams 1.3 and 0.7 meters. There's no axial force and no transverse stiffeners, and the boundary conditions are pinned as well. So these are the material properties which were measured through coupon tests and were employed in the numerical model. We used the same model as I explained it before, so with shell and solid elements and with this optimized mesh. So these are the buckling shapes for these three joints, and we consider an amplitude of DC over 200 as well. So this is a comparison of the moment versus the displacement on the tip of the beam. So you can see there's a very good agreement, especially for the initial stiffness. And as normal, there's a difference in the maximum value of the moment. This is for the second joint. Again, a good agreement between numerical and experimental results. This is for the double-sided joint. So here we have a discrepancy, difference in the initial stiffness, but we can say that the overall behavior is very similar between the numerical and experimental results. We also selected two joints from Klein, roller profiles in S275. And so here you have this table, all the geometric properties, and it's pinned boundary conditions as well, and with no actual force and transverse stiffeners. Okay, so we use the same elements in the same mesh, displacement control analysis, and for the material properties, since the authors doesn't give the whole curve, we use the values for the ultimate strength and the yield strength to determine the curves according to the quadlinear model. So you can see as well that there's a very good match for these two joints as well. We also have joints in high strength steel, so it's for welded profiles from Sandra Jordão. So it's 2 external nodes and 3 internal nodes, which the configuration are shown here. So these are the materials properties which were applied, the corresponding mesh, and the boundary conditions are pinned as well. So we can see that there's a very good agreement as well of minus than 3% difference for the maximum moment. The largest difference is obtained in the corresponding displacement. For this case as well, we have 1% difference for the small beam. For this case as well, 4.2%. There's a very good agreement between the numerical and the experimental results. And for this one as well, we obtained very good results considering the perfectly plastic behavior, elastic perfectly plastic behavior. So this is the strain distribution in the center of the web panel. So these are cuts which were done in the numerical model. So this is a comparison. The dotted lines, the lines with dots are the experimental, and the dashed lines are the numerical. So there's a very good agreement as well. On the top you have the strains before the maximum load, and on the bottom after the maximum load. Here as well we have a very good agreement, especially before the maximum load. So for all the joints, the results are pretty good. So we've conducted parametric studies using these validated numerical models for the cohabitation and cohabit compression, totalizing 936 simulations. So we consider different material models as shown here. And the objective is to compare with theoretical models and evaluate the expressions available in the codes if they are suitable for high strength steel, the S690. But today I will be focusing on the second part, which is the colloidal shear. So we started with the one-sided joint with 160 simulations. And 7 columns have been selected and 3 aspect ratios. So the objective is to evaluate the influence of the cohabitation and compression, to evaluate the influence of the actual force, and compare with different software and different design codes. It's considered elastic perfectly plastic material behavior. This is for rolled sections. and still S275. So we have 4 sets with no stiffening and no actual force, a second set with actual force, 3 different values, with a set with transverse stiffeners, and a set with transverse stiffeners and relevant actual force. So the moment ratio, as I said, is based on this 5% limit of the plastic strain. The moment is the total moment applied to the beam, and the rotation is the rotation of the joint. So it's a corrected value, which excludes the column bending and the shear deformation. So on this plot, you have the division we have for the column. So we split the column in these different parts, these 5 different parts. And on this plot, you have the evolution of the plastic strain in every part according to the rotation of the joint. So our criterion to define the maximum load is when this value is reached, when, whatever the region is reached. And on this plot, you have a comparison between different criteria for the maximum moment, for the moment resistance. So on this plot, you have a summary of 3 columns as an example, and the dots are the moment resistance of each joint. And here you can see the difference between them with actual force, which are the colors, and with stiffened and unstiffened. So the difference between full and dashed lines. So this is a comparison between the results obtained from this model and from standards, so the Eurocode and the new Eurocode, and with Idea Statica, which is the software we are comparing, with different meshes in order to compare the moment resistance for these all sets. Okay, so as a conclusion, we can say that Idea Statica produces a small scatter, which is a very good sign. A mesh refinement and the additional safety factor will improve the results. And the design codes are normally conservative, and the new Eurocode is not offering a major improvement for these predictions. And finally, this criterion of plastic strain is highly dependent on the mesh size, as I already shown in the previous plot. So these are some publications I've done. So this research is funded by the FCT. So thanks to FCT, and the framework of this thesis is within Idea Statica, cooperation with Idea Statica and the University of Coimbra. That's it. Thank you.
Well, thank you very much for the presentation. So I believe there are really a lot of experts on this, so they will have a lot of questions for you. You can start with.
Thank you for the presentation, Fernando. I see that you have a lot of work in finite element modeling and Python scripting. Good work. I have some questions for you. I pointed out some slides. If you could please move to slide 12. My question is, why haven't you considered all 3 axes of symmetry for the column web components?
So this is a good question. Actually, we could have considered this symmetry plane for the column web intention, but since we have the column webbing compression, the shape of the imperfection is not symmetrical to this plane. So that's why we consider only these 2 planes.
Slide 16, please. here, why didn't you use beam elements outside of the core region of the joint? And what are the main advantages of using the shell elements here in this case?
So we actually tested this option of considering beam elements, but we have the advantage with shell elements of extracting paths along the whole length of the cone of the beam.
Paths effectively?
No, paths, section cuts. So you can extract section cuts of strain, so you can have more information, even if the stresses and the strain in this region aren't that significant, but we can have it. And the advantage of considering shell elements is saving time and additional effort and space, because we have less nodes, so we can have like a finer mesh, even a finer mesh in the solid core, since we are saving elements in these outside regions.
Slide 19. Why did you use rigid body constraints here in the beam for all linear buckling analysis? Okay, so we consider these rigid body constraints to have this effect, so to have only the imperfection localized on the web panel. So we did some previous tests without this rigid body to the whole beam, but we have modes, for some first modes in the beam. So that's not what we want. We want the imperfection in the web panel. So since it's an automatized process done through Python, so we did this approach.
What is this?
This is without stiffener, and this is with stiffener. I cannot see very well.
So you have done the linear analysis. And then what was the influence of these in your results? So my question is, because this is a standard pattern to take the imperfection into account. But did you try to assess the influence of this? So you have basically at the end you have two dimensions for the imperfections. So you have DC divided by 200 and DC divided by 400.
This is for the co-orientation and compression. For this, for the whole model,
what was the influence of this in your results in a global way?
So of course, this perfection shape will change the moment rotation curve. We did at some point we did a test with different amplitudes, which also has an influence, but it's not depicted here. Yeah, that's a good question. We could explore more this, like use different imperfection shapes and try to test the difference.
Because it probably also depends on the thickness of
In this case, we want to have an imperfection in the compression part. So, in this case.
Yeah, we can move on with other questions. So you have
next slide. I would like to know what are the main outputs that you can extract using Python script.
Okay, so we have several outputs we can extract, like the moment rotation curve, some section cuts. We can extract the displacement and stresses for the nodes along this whole solid core. But what interests most us on this study is the web panel. So that's what we're focusing. And we generate text files with these results. So later we can process them and plot and compare the results.
And, moving to the end, to slide 46, about the results with idea statica. I see that you compare several models within Idea Statica and the Eurocode 3, but did you compare with your Abacus model?
Yeah, so sorry. This is not was not well explained.
Okay.
So this is the moment resistance obtained in the finite element method. So the solid model. So this is the ratio actually. So all these plots are the comparison between the numerical and the results from the method. So this is a comparison of the Eurocode from Idea Statica.
So all of them are, or almost all of them are below 1.
And as you refine the mesh, you get closer results to Abacus Idea Statica.
Moving to slide 48.
Okay.
You highlighted that the 5% criteria for plastic strain depends on the mesh. But have you considered other criteria?
Okay, so we use this criterion because this is employed in the new standard, so the new Eurocode 114. And actually on this plot, you have a comparison between different values. So we have this of fraction of the initial stiffness, the comparison between this value, so the 5%, and the second stiffness. So the values do not differ too much in terms of resistance. In terms of rotation, there's a large difference, but in terms of maximum value, so for the load, it's below 5% generally.
And with regard to the Eurocode 3 part 114, it's a pretty recent code with guidelines for finite element design, and in which way your work could contribute to improve this new code with proposals?
So basically on the evaluating the numerical results, like ways of extracting the numerical results, the numerical model, guidelines for numerical modeling, and also this criterion of 5% was something that a bit shocked us a bit. We weren't expecting this. So identify failure modes, which is something that is not too much developed still. So this way, and also to develop, to compare results for high strain steel, which aren't that too much explored so far.
Thank you, Fernando.
Yeah, I just have a question similar to Professor Abel's. When you did the calibration of your model, did they mention anything about the fractions?
Sorry?
When you did the calibration of your numerical models against experimental stuff from the literature, did they mention the fractions? Did they measure experimental fractions?
So from Sandra Jordão,
is there any mentioning of
she measured the final deformation of the joints and tried to input on her models a similar shape to obtain that, but it wasn't measured before the test, it was after, and she tried to.
your model in the first bucket modes gave the good results, and you don't know what they did, so maybe.
These are the booking modes. We follow the guidelines for this case.
What about residual stress?
Yeah.
Okay, so
That's a second one, because here we were following the geometrical nonlinearity. It's more like a material nonlinearity. So have you ever tried the residual stress?
yes, we did a couple of tests with residual stress residual stress model from the CCS and new models which are presented in the literature, but the difference in the moment resistance was insignificant. In this case, we are considering implicitly, since we are considering an imperfection of dc over 200, which is implicitly covered here.
And even for the high strength steel, it was residual stress again.
I first want to congratulate you because I know you've been doing this hard work, staying much after working hours and so on. So congratulations first. And I have that small questions. One would be, why did you consider the elastic perfect plastic material in the validation? So you were considering the quadlinear model in some tests, and then you switched to elastic perfectly plastic model. What was the reason for that?
So for this case, we had better results for this perfectly plastic behavior. This was a trial we did, and this may be attributed to the failure mode probably. So for this joint, and yeah, we had better results considering this behavior.
Yeah, actually, that was why I asked you, because I've seen this quadlinear model developed by Gardner, and that is mostly for conventional steel grades. For high steel grades, as we're showing here, the plot does not really match because I tried it on the same material.
No, but for this case, for the validation, we use the proper material properties. So
Exactly.
the coupon test, yeah, which are here.
Okay.
So this may be attributed to some scatter in the columns, I don't know, the experiment.
Okay, this was a general question. You were mentioning that you had applied some relevant axial. So what's this relevant in slide number 43? But you could answer it.
Okay, so this is just a ratio of the column actual resistance.
The value.
So 0.3, 0.5, and 0.7. So this is just to compare to the Eurocode. Since the Eurocode says there's no difference
So you try to play with the ratio of this load to the plastic resistance in the cross section. So when the values you used were 30% or 50% and 70%. Well, did you see a significant difference between the results with the values?
You can compare, for example, for unstiffened. So the black curve is without actual force. The red is with 30, the blue is with 50, and the green is with 70. So there's
It was more or less about 25%. Also when the axial load was about.
and even with 30 and 50%, there's a significant difference for some cases.
In slide number 44, just one slide actually. This 5%, yeah, I've tried to read part 114, and part of the work that I'm doing is also related to this, and I also want to question it. Yeah, my question here is, which portion, which part of the cross-section do you consider is the most relevant? Because I see you have several curves as you took several parts of the cross-section. Which part was crucial in either all the way with compression, tension, or shear? And how did you take this value? Did you take the average, or did you take the first incidence of the 5% plastic strain occurring in those regions?
It's the maximum.
So the peak, whatever value when it reached 5%.
Yeah, the peak. Yeah, so answering your question, so I think the most relevant for these simulations we've done are the S1RR, which are close to the beam, and the wet panel. So in this intersection, This is where there is like most stress concentration, and this is where the largest strain and stresses occur. For tension, for sure it's here, because the failure mode is due to necking. And for compression, it will be in the web panel.
Last two questions. When you mention idiostatic charts, what does it signify?
Sorry, yeah, I did not explain very well. So this is just a Richardson extrapolation, which is a Richard extrapolation. It's a formula to determine the optimal value for the mesh size. So this is more or less similar. You can see the results to the refined mesh. So this is a calculation based on the results to determine the optimal value for the mesh size.
It's like an ultimate. If you have two values of the mesh, for example, default and then a little bit refined, then you can calculate like it's an infinite mesh. There's a formula. You calculate as if you had already the perfect mesh, which is like millions of models.
And it gives you the approximation.
It is. It's a lot in
In terms of this mesh, when you say that it's mesh dependent, it's 5% value. Could you say how it is mesh dependent? Say for coastal mesh it goes like this, for final mesh it goes like that.
So we did several attempts on that, like to check if you refine it will decrease the value, if it would change the position, like if it would appear in a different position so on this map, for example. Change
position.
Yeah, it can change. We did some tests of removing a small line of elements in this intersection because we thought this could be due to stress concentrations there, and but we could not find an answer, and this is something we need to explore still. But we have already identified this problem, which is very, very significant. The difference is very, very large.
Large in terms of
Rotation.
rotation, not up. That would be all. Congratulations again, and thank you. Questions?
Any other questions? We can receive questions from the external audience.
Yes, yes.
Yes.
What are you going to questions.
Okay, so if there are no more questions, so congratulations for your presentation, and I wish you all the best for the rest of the work. And probably we will see you again in next week. Next week. So thank you very much.